Fujita type critical exponent for the semilinear parabolic equation. And in first lecture, we will discuss about classical Fujita results and some of their extensions, including sign changing solution. And in the second part, we discuss about the non-local extensions of Fujita type results, and also about semilinear heat equation with forcing term. In this case, we had a definitely different critical exponent defined by Levine, Wendel, and Jung. And yesterday we discussed about Fujita type results on the exterior domain, and we discussed about the Dirichlet problem, and Neumann problem, and the Robin problem. And today it's a good time to discuss about critical exponent on the bounded domains. Yeah. Today's presentation contains two parts. First part, introduction, and second one, main results. In the second part will be about our result. And let us start also with a Fujita's paper. Sorry if I repeat every day. And he considers this semilinear heat equation. There is some new participants, and maybe it's good if I repeat again. In 1966, Fujita considered this kind of semilinear heat equation with non-negative initial data. And he interested on the global existence and the blow up of this solution of this problem. And he gets the following results. When P between 1 and 1 plus 2 divided by n, he proves that the considered problem does not admit a global in time positive solution. And if P greater than these numbers, then for sufficiently small initial data, there exists positive in time global solution of the semilinear heat equation given by on the whole Euclidean space. Yeah, and the critical case was proved later by Hayakawa in 1-2-dimensional case, and later by Kobayashi, Shirawa, Tanaka for multi-dimensional case. And in this case, they also proved that this critical case also belongs to this first part. It means that in this case also for any non-negative initial data, there is no global in time positive solution. By non-existence, I mean here the solution blows up infinite time. Yeah, and this number is said Fujita type critical exponent. And later in 1988, Peter Meyer considered the extension of Fujita results on the k times half space, where Rk plus can be defined by this formula. And he proves that the critical exponent in this case will be defined by this number. If here k goes to 0, and in this case this set coincides with the Euclidean space, then we have classical Fujita critical exponent. And later, Katerina Bendel and Howard Levine consider the same problem on the exterior domain with the homogeneous Dirichlet boundary condition. And he proved that the Fujita critical exponent the same for the exterior problem, because in the previous case it was a little bit different critical exponent, but here it will be the same with the Fujita critical exponent. And later Levine and Chan consider a Neumann problem, and here they also prove that the critical exponent is the same. And later, Raoul consider a Robin boundary condition. And in this case, also, the critical exponent will be the same with the Fujita critical exponent. Yeah, and before formulated this problem, let me show one example on the bounded domain for the semilinear heat equation, because here we have a little bit different nonlinearity. Here we have some weight dependent on the time variable. If we consider the same problem as a Fujita on the bounded domain, let us consider the heat equation. On some bounded domain of Rn with smooth boundary and with Dirichlet boundary condition. Then, if the initial data bounded from below some constant, for example, and p any number greater than 1, then for this problem, for any p, there is no global in time solution, positive solution. For example, we can consider this kind of differential equation of first order. With non-negative initial data. Then the solution of this problem can be represented by this expression. And if p greater than 1, then this part will be the positive. Then if t goes to capital T, then there will be the process blow up. And this function also satisfies this one. And on the boundary, it will be the non-negative, positive. And the initial data also can be defined by some constant. And if you assume some restriction for the initial data, then we can arrive that, so for any p, there is no global in time positive solution. If p less than 1, then for some sufficiently small initial data, there is a global in time positive solution. And if we consider the same problem as a Fujita in bounded domain, the critical exponent will be just 1. And in 1990, Peter Meyer considered this kind of perturbation of Fujita problem. Here, h of t depends only on the time variable. And on the bounded domain from Rn. And in the boundary, consider Dirichlet boundary condition with Cauchy initial data. And he assumes that this function h of t bounded from below and above by exponential function. Then, yeah, here, let me write again. Let's suppose that lambda 1 is positive, T1 x was positive, and it is the first eigenvalue of Dirichlet Laplace operator. Phi 1 is a first eigenvalue of eigenfunction of Dirichlet Laplace operator, and the lambda 1 corresponding first eigenvalue. Then Mayer proved the following results. And if P greater than this number, here 1 plus beta divided by lambda 1 is the first eigenvalue, then there is the global solution for some sufficiently small initial data, and its supreme norm is finite for any time. And also subcritical case, if P between 1 and 1 plus beta divided by lambda 1, then any non-trivial solution of the semilinear heat equation blow up in finite time. It means that the norm of u by x goes to infinity if t goes to some capital T star. This C continuous function. Yeah. Here supremum. Okay, let us prove. Let us give the proof of this statement in more simple, by the more simple approach. We essentially use the comparison principle. If you remember, in the first lecture, we give a comparison principle for the semilinear heat equation. I can repeat here. Here we can put any nonlinearity, for example, local Lipschitz. And we can also consider if this one like this inequality, and second one satisfies this differential inequality. And it's also zero in the boundary. Then if initial data satisfies this inequality, then the solution also satisfies it. This inequality. This is some generalization of maximum principle for the parabolic equation, and we essentially will use this fact. Then let us consider this kind of function, v of xt, here a of t and zxt. Here we have explicit representation of z of xt. This can be defined by this one, the exponential function. Here lambda 1 is the first eigenvalue of Laplace Dirichlet operator, and phi 1 is also first eigenfunction of this problem, Laplace Dirichlet Laplace problem. Then this function z will be the solution of the linear heat equation with Cauchy-Dirichlet condition. And also, we suppose that a of t is a solution of this kind of first order ordinary differential equation with this kind of nonlinearity. And we also assume that the initial function is strictly positive. Then it's not difficult to find that the solution of this problem can be represented by this expression. Here, a0 is the initial function. And here we have also the norm of z by x, supremum norm of z. Okay, then then we calculate the function v. The function v. We put the v into the equation or, and from here we get the first order derivative of a of t, and here z, and the minus h of t, here a power p, z power p. because if we use this heat operator to the function z, then it can be equal to 0 because it's a solution of linear heat equation. Then we have only these two terms. And from here, we can rewrite this expression by this one, because instead of a first order derivative of a, we can put this term, this nonlinear term. And then we have this one instead of first term, and this one is a second term. Then we can rewrite this one also by this term. And inside of the comma, we have the supremum norm of z is power pi minus 1 and z power pi minus 1. And here we have the supremum norm. Then in every time it will be the greater than this one. Yeah. Then finally, this term will be non-negative for all t. And we have this inequality. It means that if we assume your initial function bounded from above by this function, then our solution will be bounded from above by this function v, this a of t and z of xt. And let us estimate this function a of t. Suppose that p greater than this critical number, and h of t satisfies this inequality, these properties. So for a of t, we have this one. This is a representation of a of t. And from here, instead of h integral h function h of s, we can put this one. Then we have this expression finally. And also we can rewrite the function z s. It was this like this form, and the supremum norm of this function will be some constant. And then we have only exponential function. And then we have this expression inside of the integral. Then we can rewrite this one by this one. Yeah, we can calculate this integral, and we get this one. Because if p satisfies this inequality, then this power will be negative. Because the p was like this. If p greater than this critical number, then this power will be negative. Then all of this expression exists for any time. It means that it's bounded from above some constant. Then finally, we have this one. And this one is bounded for any time. It means that the solution of our problem exists globally for this kind of p. Okay, next, let us prove the blow-up part. Again, we can consider this kind of function. W here, b of t and zxt. This is still solution of the linear heat equation with Cauchy-Dirichlet conditions. And b of t can be defined by this expression. And it is a solution of this first order differential equation, nonlinear differential equation with strictly positive initial data. Then we can calculate, we can put this function v into the our equation. And if we assume p less than this critical number and h of t satisfies this property, and calculating this one, we have here first derivative of p of t, here z, and minus h of t, b power p, and z power p also. And also here, z satisfies the linear heat equation, and the derivative of z by time and by x 2 times will be equal to 0. And also we can rewrite this expression by this one. And also, yeah, it comes from equation of equation for the function b, because b was a solution of a first order differential equation. Then instead of this one, we can put this one. Then we have this kind of expression. And now we will estimate inside of the comma only. Then we have finally this one. And we suppose that this P satisfies this condition here. This one, less than this one. Then the power of the exponential function will be positive. Then for sufficiently small, sufficiently large time t, the right-hand side of this differential equation, differential inequality, sorry, will be negative. It means that V satisfies this kind of differential inequality, W. And if we suppose that initial function bounded from below by this function, then the solution of our problem and the solution of this problem satisfies this inequality. It means that this W is a sub-solution of our considered problem. Then using the comparison principle, if here we, sorry, let us recall here, yeah. If t goes to some point, then there is blow up, finite time blow up. It means that the function W blows up at finite time. Then here is also at finite time, this function blows up. It means that this one is also blows up in a finite time. This proof our theorem, second part of our theorem. And it means that there is a critical exponent depends on first eigenvalue. It was a new phenomenon. Yeah, and later there is some improvements or generalizations of these results. For example, Bendel and Pozio and Tessé, they consider the same problem as a Mayer on the hyperbolic space, and they get almost the same results. But if they also prove that in the critical case, the considered problem has a global in time positive solution. Because in the case of Fujita problem, the critical case was about a blow-up solution, but here, critical case belongs to the global existence case. And also in this paper, Chinese mathematicians considered the same problem, but for the system of semilinear heat equation. And they also get the similar results, critical exponents. Also, there is paper by Castillo, Loayza, and Paishao. They also consider system of parabolic equation on general domains. Yeah, and there is also non-local extension of Mayer's results, but here a little bit different. In 2019, Zhang and Ni considered this kind of problem. Here, time derivative d alpha is a Caputo fractional derivative. I can write here the definition of this operator. First, E gamma u, it's the integral operator by Riemann-Liouville. The integral from 0 to x at a minus s power gamma minus 1 and u of s ds. This is a fractional integral in the sense of Riemann-Liouville. And this one, the alpha u, this is a Caputo fractional derivative. It can be defined by this expression. Inside of this integral, we can put a derivative by time. And this is operator. It's called Caputo fractional operator. Yeah, and Zhang and Li consider this kind of problem. Here, nonlinearity part also contains non-locality, because here integral by time. And they assume that alpha between 1 and 0 and 1, and gamma also between 0 and 1. And they obtained two results in the case when alpha greater than gamma and alpha less than gamma. Let us formulate these results. Suppose that this alpha greater than gamma and U0 from space C0 with compact support. And if P less than 1 divided by gamma, and the initial function non-negative and non-trivial function, then all solution of our considered problem blow up in a finite time. And if P greater than this number, 1 divided by gamma, for sufficiently small initial data U0, there exists a global in-time solution. In this case, the critical exponent depends on gamma. And if alpha less than gamma, and the U0 is the same as with this theorem, then there is another exponent depends on gamma and on alpha. And they suppose that in subcritical and critical case for non-negative, non-trivial initial data, solution of the considered problem blows up in finite time. And he also proves that if P grids this critical exponent, greater than this critical exponent for sufficiently small initial data, the solution exists globally. And all of these results will be was about semilinear heat equation on the bounded domain. Now let us consider the semilinear heat equation on the annulus domain. In 2022, these Arabic mathematicians Jalali and Samet they consider this kind of semilinear parabolic inequality given by the formula 2. Here in the right-hand side, we have this kind of term, singular term. Here capital A is the annulus domain. This is inside of this is here. This is inside of two balls. Yeah. Here a rho is a strictly positive number, p greater than 1. And this problem, this equation considered under the two type of inhomogeneous boundary condition. First one is a Neumann type boundary condition, this one, and on the boundary of ball B2. And second one, a Dirichlet boundary condition. And they prove the following results. Started with two-dimensional case. If this boundary function integrable on the boundary, here just mistake, should be f also. And the integral of f is also strictly positive on the boundary. And if p less than this rho minus 1, then they considered semilinear heat inequality with Neumann or Dirichlet boundary conditions does not admit global in time weak solutions. It means we have blow-up solutions only. And if p greater than this rho minus 1, then the considered two problems admits global in time positive solutions for some boundary function f strictly positive. Here also by global solution, they mean stationary solution of the considered problem. Yeah, here also the critical case was left open. They don't study this case. And using our technique, which we discussed in the last lectures on the whole Euclidean space and the exterior domain. Here we will develop our approach on the annulus domains. And it's our main result. It was recently published in the Journal of Mathematical Analysis and Applications with my former PhD student, Meirhan Burhan also. And here we suppose that n started with 2, p greater than 1, f is an integrable function on the boundary, and if satisfies, if integral of f on the boundary is strictly positive, and p equals to critical case, rho minus 1, then the Dirichlet and Neumann problems for the semilinear heat equation does not admit the global in time positive solution. It means in this case also the critical case belongs to the blow-up case. Let us give the proof of this statement. We consider for sufficiently large t and r this kind of function. This is a test function. Here mu of t has this kind of explicit representation. And here the power L greater than this number, p plus 1 divided by p minus 1. And here function depends on the x variable, satisfies this kind of properties. This one is this function between 1 and 0, and it has this support, this kind of. And also it's equals to 1 inside of this annulus. And outside of this ball with radius 2, it's 0. And let us formulate some lemma. And for the function psi of x, we introduce it in this form by a logarithmic argument test function form. And we suppose that this function capital phi has this kind of properties. It's 0 if z between -1 and 0, and it's increase when z between 0 and 1 divided by 2. And if z inside of this range between 1 divided by 2 and 1, then this function equals to 1. And also we suppose that the first derivative and second derivative of this function is bounded. Then for the this Laplace operator of the function xi, we have this kind of estimate from above, defined by formula 7. And we will skip the proof of this lemma because it's quite easy. You can use just radial form of Laplace operator, and you can take the first order and second order derivative of this one, and using these properties, you can have this inequality 7. And this is the second lemma. Let us consider this as the same function, phi, defined by this expression 8. And for sufficiently large capital T and capital R, we define this integral operator, I1, defined by this expression. This one contains only test functions and this kind of singular term. Then this integral can be estimated from above by this term. It depends only on capital T. Here, S is a positive number. And we also define the integral I3. It can be represented the same way, but here we have only, instead of the first derivative by time, we have a Laplace operator. And also we can estimate this integral by this term. Here, capital T, and inside of the comma, logarithmic functions by R. And let us give some simple proof of this statement. We can rewrite the integral I1 by this form because our test function can be written separately by x and by t. And we can calculate each one differently. This one from the 5. 0 was the property of this test function by x. Using these properties, we have for this term, we have this one, this integral bounded from above by constant. And the function depends on t, can be explicitly calculated. And we have, for this integral, we have this one. And using the 11, this one, sorry, there is some mistake. Yeah, not this one. Here we have this one, and using this factor, we can estimate this integral I2, this part. And finally, we have this formula. This formula, 9. And the estimate for I3 can be proved the similar way. We will skip this proof. And now let us prove our theorem in the case of Neumann boundary condition. And we can multiply our problem by test function phi, and integrating by parts, we can obtain this kind of inequality. And sure, we can use the Young inequality to the right-hand side of inequality 14. Then we have this one, this one. This is the same term as the nonlinearity part of our differential integral inequality, this one. And also for the second term, we have this one. And we have the some estimates of this integral I1 and I3 in the previous lemma. And instead of epsilon, we can put p divided by 3. And finally, we have this kind of integral inequality given by the formula 15. Then using the results of the previous lemma, we can rewrite this inequality by this expression. And if, as R and capital T is a sufficiently large number, we can, instead of R, we can write capital T. Then if rho equals to pi minus 1, and the integral of the f on the boundary is strictly positive, then passing to the limit when capital T goes to infinity, we have that the right-hand side of this integral inequality goes to 0. And this is a contradiction with our assumption, because we assume that the integral of f is strictly positive. It means that in this case, the considered problem does not have global in time solution. And let us give the proof for Dirichlet boundary condition case. And for this reason, we consider this kind of test function, psi. And here we have this harmonic function. Differently than the previous approach, a little bit differently. The harmonic function has this kind of form. In two-dimensional case, it can be defined by a logarithmic function. And started with three-dimensional case, it can be written by this expression. And from here, we have that this harmonic function is non-negative. It's sure, it's harmonic and satisfies on the boundary, Dirichlet boundary condition. Then we formulate the first lemma for the function psi on the boundary gamma. We have this kind of differential inequality. So it means that the normal derivative of function psi non-positive on the boundary. Let us give the short proof of this statement. We use this fact because we assume that inside of this unknown domain, our test function equals to 1. Then we can get a first order derivative of function psi2. Finally, we have this one. This one equals to this one. Then we can calculate on the boundary this term. Then we have this one here. Capital C of n is a positive, but here we have the sign minus. It means that the normal derivative of function psi2 is non-positive. Non-positive on the boundary. Yeah, this one. This is a second lemma about some integral inequality for the integral I1 and I3. Here we also define the integral I1 by this expression. Then this integral can be estimated from above by this term, capital T. And similarly, for I3, defined by this expression, we have this kind of estimates from above. Also, it can be proved similarly. Here, we can write each one differently by x and by time, and we can easily calculate this term. And also using some properties of harmonic function and some properties of the this test function. Yeah, this kind of properties we have. We can also calculate the Laplace operator of the function psi2. And finally, we can estimate this one by this one. And finally, we get the last expression. Finally, this one can be estimated by this this term here, logarithm r power minus p divided by p minus 1, and also this the negative power of the r. Okay, and combining the above calculations, we can complete our proof. Yeah, and let us now give us a proof or theorem in the case of Dirichlet boundary condition. Yeah, here also we can multiply our equation by the test function psi, and we can integrate by part, and finally we have almost the same inequality as this one, and a little bit differently here. Instead of phi will be a normal derivative of test function psi. Yeah, and this one. Yeah. And instead of epsilon, we can put also p divided by 3 and calculated this integral inequality. And finally, we have this this integral inequality. Here, I3, I1, and I3 we introduced before in this lemma. Then to the right-hand side, instead of the right-hand side, first we calculate this term. Here, because here psi depends on the x and on the t, but this boundary function depends only on the x. Then we can write instead of this term, and we can easily calculate this one. And finally, we have for this integral, we have this one. And here instead of this term, we can put this calculation, this inequality. Then using our previous lemma about I1 and I3, we have this integral inequality finally. Yeah. And also, if here instead of R, capital R, we put capital T and passing to the limit when capital T goes to infinity, we have that the right-hand side of this inequality will be goes to 0. This is also a contradiction because we assume that in the theorem the boundary integral of the function f strictly positive. This proves our theorem, and here let us come back to the formulation of the problem. Sorry. Yeah. Here we consider only Neumann and the Dirichlet boundary condition. Also, one can investigate, for example, with a Robin boundary condition, or also there is a another interesting problem. We can change this term. Also, we can put here some non-local term like this, and in this case, also it gives some effect to the critical exponent. And also on this direction, a lot of interesting problems, and a lot of peoples from the different country investigated this direction. And it was the last part of my lecture, and the proof was the last part of my presentation. And thank you for your attention. If you have any question or comment, welcome. Yeah, thank you.
When you use any infinity function for the HT or
See, infinity function. Because this weights give some effect if it has some little bit singularity at the infinity or at some initial point. Yeah, if it's a very nice function, probably they will not give any effect. Yeah, oscillating functions is also bounded functions, right? Here, if you're working with a critical exponent, give effect only polynomial type functions. Yeah.
if you work with numerical methods to solve these operator equations numerically, do you see some difference with respect to your critical parameter? What happens with stability or convergence order with these methods?
Yeah, thank you. It's a good question. There is some guys who interested on this kind of problems, but it's very difficult because if you have a blow up, it's very difficult to get some stability if you investigate numerical solution. But some guys investigate this kind of problems, and they prove that this scheme is not stable. It means it's very close with a blow up.
You describe the Mayer result with the time-dependent right-hand side. You use the upper bound, but have you also used the exponential lower bound in the proof?
Yeah, it's a Mayer result. You mean in the proof?
Yeah, you showed us a proof, but there was explicit mention of the upper bound, but was there also the use of the lower bound?
You mean
this HT was bounded exponentially from below?
Yeah.
And above.
Yeah, when we prove the global existence, we use upper bound.
Yeah.
When we prove blow up solution, we use lower bound. Yeah.
And that's a quite specific time dependence.
Yes.
Is there anything for other functions of the time on the right hand side?
Yeah, if you put, for example, a polynomial function, it does not give effect. It will be the same with this one. For any p, there is no global solution.
Okay, the same spirit. If you modify the right hand side with Mayer, it's the time function. In a Euro program, it was a function of the spatial variable.
Yeah.
Has anybody considered a combination of the two, something which would depend on both space and time?
Yeah, probably. Yeah, it's a good question. Maybe it's we can consider, yeah, in the future our research. because in this case, the critical exponent does not depend on first eigenvalue, only on the power of this term.
So let's thank Day4
Thank you.
for this lecture and the whole program.
Thank you.